So here we are on page 17, and our job is to graph a rational function. So I'm going to list down several steps as well as an example at the same time. To kind of keep my information in order, I'm going to crease down vertically so that on this side I will write down the steps, and over here I'll write down our example. If we have r of x is equal to x minus 1 over x squared minus 4, our job is to graph that. My suggestion is that the first thing that you do is to factor both the numerator and the denominator. The purpose is so this will allow us to find the domain, and it will also, and that's when we use the denominator to find the domain. We can also use the factoring to check for holes. So if we rewrite r of x in factored form, I'd get x minus 1 at the top, I get x minus 2 at the bottom, as well as x plus 2. So we can quickly see that there are no holes since nothing is crossing out, but we can find the domain. So domain is going to be from negative infinity to negative 2, from negative 2 to 2, and from 2 to infinity. Remember, we set that denominator equal to 0 and solve. From this one we get x is equal to negative 2. From this one we get x is equal to 2. Putting them in order of a number line, we can see that our domain is everybody except for these two right here, because we cannot let them equal, allow the denominator to equal to 0. And like I said, we found out that there were no holes. Second thing we want to do is to write our rational function in lowest terms. In other words, if we had a hole, we want to go ahead and cross out the factor from the top and from the bottom. We don't have that, so ours is already in lowest terms. So r of x is already in lowest terms of x minus 1, x minus 2, x plus 2. Step 3, our job is to find intercepts. To remind you that you want to find the y-intercept. That is when we allow x equal to 0 and solve for y. And then we also want to find the x-intercept when y is equal to 0. For this one we use only the numerator. So let me show you what I'm talking about. For the y-intercept, let's let x equal to 0. So r of 0 is 0 minus 1. At the bottom I have 0 minus 2, 0 minus plus 2. At the top I get negative 1. At the bottom I get negative 2 times 2, which is negative 4. So my answer is 1/4. That means we have found the y-intercept is the point 0, 1/4. Likewise, when we let y equal to 0, remember what I said, just use the numerator. So I'm going to get my x minus 1 and I'm going to set that equal to 0. Notice this is only the numerator. When I'm solving, I find that x is equal to 1, which means we have found the x-intercept to be the point 1, 0. So these are points we're going to use on our graph. So I want to make sure I can find them later. The next thing we're going to do is we're going to find the vertical asymptote. Remember, we find this from the factored form. And more importantly, it's only when the denominator is equal to 0. So in our case, when we have r of x is x minus 1 over x minus 2, x plus 2, We're only looking down here at the denominator and we're setting it equal to 0. So we're going to find x is equal to 2 and x is equal to negative 2, and these are our vertical asymptotes. So again, I want to find these and graph these when the time comes. Step number 5. Our job is to find horizontal asymptotes. Remember, here we're going to look at the degree of the numerator compared to the degree of the denominator. In our case, we have r of x is equal to x minus 1, so that has a degree of 1, over x minus 2, x plus 2. And remember, when I multiply these two, I get x squared. So the degree at the bottom is 2, and the degree at the top is 1. Because we are bottom heavy, we know that the horizontal asymptote will be y is equal to 0. We learned that in our last lesson on Wednesday. From here, the next step we need to do is actually graph. And we can also use a graphing calculator to help us get the details or the right picture. So I obviously don't have enough room here. I know you do have a grid that was given to you in class last time. We're going to put it right here. I'm going to tape it so that maybe we only tape it on one side, either on this side or on this side, so that I can still find my information about horizontal asymptotes. So let's go ahead and use all the information that we found in order to graph. So one of the first things I'm going to start graphing is by using our horizontal asymptotes. So our horizontal asymptotes, I'll move this up just a little bit more. Our horizontal asymptotes were at x is equal to 2 and x is equal to negative 2. So I'm going to draw my vertical asymptotes right here at x is equal to 2 and x is equal to negative 2. I'm also going to start with my horizontal asymptote. So we already did the vertical asymptotes, and now I'm going to do my horizontal asymptote. When I do that, we notice y is equal to 0 is just the x-axis. So I'm putting my dashed line so that you can see that I did graph it. Let's put our points together. So if I put my points, I get 0, 1/4, so it goes through this point. And my x-intercept is at 1, 0, so it crosses this point. What we're going to find out if you put this into a calculator is that this graph comes through here, goes through my y-intercept, through my x-intercept, and comes down this way. But that's not all. Notice that our domain says there's still stuff over here when x is greater than 2. And we're going to see, and I'm going to show you why this happens in a minute, but it actually looks like this. And on the other side, it's going to be over here. So let's talk about why that happens and how did I know. The last thing I'm going to do is just highlight my graph so that we can see that my graph looks like this in between my vertical asymptotes and horizontal asymptotes. And like I said, I'm going to tape it on one side so that we can still see the information underneath. You can see the information right here. Again, I will scan my notes in so that you can see all my notes as well. The question was, how do we know what it looks like at the ends? So at the ends, what we're going to find is look at our long run behavior. So take a look at r of x one more time, and this time let's just look at our x at the top and our x squared. And notice I left off the -1 and the -4. I'm just looking at these two guys. If I do that and I look at the reduced form, it looks like 1 over x. And that's our parent function, and our parent function says it looks like this. So at the end, notice we said we ignored the 1 and the 4 is because we know the x's are getting really big and the 1 or 4 are small compared to x being very big. So that's how we're seeing this part right here looking just like 1 over x. Let's go to page 18, and we're just going to do a couple more examples. Just going to do a couple of examples here on page 19 and 20. On page 19, let's do example number 1. Our job is to graph r of x, where r of x is equal to x squared minus 1 over x. Remember, the first thing we're going to do is factor, so x plus 1, x minus 1 at the top, and just x at the bottom. From here, the first thing we want to determine is domain and holes. And we can see that there are no holes because we don't see anything crossing out. So no holes. Our domain, we're looking at the denominator, is x cannot equal to 0, so our domain would be from -infinity to 0 and from 0 to infinity. Step 2 is to write it in reduced form, which it already is, so I'll just rewrite it. R of x is equal to x plus 1, x minus 1 divided by x. Step 3 is to find the intercepts. So to find y-intercept, we let x equal to 0. But because of our domain, so I'm going to write that down, not in domain, then we have no y-intercept. No y-intercept. For the x-intercept, we let y equal to 0, and essentially we put just the numerator, which is x plus 1 times x minus 1, and we set that equal to 0. And we solve those. Solving, I find that x is equal to -1 and x is equal to +1. So we have two x-intercepts. One of them is -1, 0, and the other one is at 1, 0. So these are points that we can put on my graph. Step number 4 is to find vertical asymptotes. And remember what we said, for vertical asymptotes we look only in the denominator. And in our case, we're going to find from here, we're looking for our VA, our vertical asymptote. We find x is equal to 0 is a vertical asymptote. For part 5, we're looking for horizontal asymptotes or oblique asymptotes. In our case, well, let's see what we have. For horizontal asymptote, we need it to be bottom heavy or equal degrees in the numerator and in the denominator. In our case, we actually have top heavy. We have r of x is equal to x squared minus 1 over x. Because it is top heavy, then we need to do long division. So to do long division, I'm going to get x squared minus 1 divided by x. X times what will give me x squared? I need to multiply times x, because x times x will give me x squared. And then I'm going to subtract. Those are gone, and I end up with just -1 down here. That's what we call our remainder. This quotient that we found up here, y is equal to x, this is our oblique asymptote. It's oblique because it has a degree of 1. So if it's top heavy by 1, then you have an oblique asymptote. If it's top heavy by 2, meaning that the degree is 2 or 3 more than the degree at the bottom, then we don't have an asymptote at all. Alright, so we found that this is our oblique asymptote. And then we're ready to go to part 6, which is to graph. So I'm going to use my other grid so that we can graph everything that we know. So we know vertical asymptote is at x is equal to 0, which is going to be the x-axis. Notice that we have an oblique asymptote, so instead of having a horizontal one, we have y is equal to x. That's going to be this diagonal. So we have our graph, vertical asymptote, and our diagonal like this. Well, if we were to take a look at our solution from long division, we found y is equal to x up here, and then we have our remainder. Our remainder is negative 1 over x, and this is a parent function. But because our horizontal asymptote is not horizontal but diagonal, we're going to actually find that we're going to have one of them over here on this side and one on that side. We do have points. We have 1, 0. So on this side, it must go through 1, 0 and get close to our asymptotes, and then come this way and get close to our vertical asymptote. On the other side, I have a point at negative 1, 0. It has to get close to the vertical asymptote as well as close to the oblique asymptote. So I'm going to put those in green again to highlight our graph. And I want to enforce that knowing your parent functions kind of help us decide what our graph is going to look like. So from here, I'm going to tape this one down. Let's do example number 2. Our job is to find the rational function equation, because now we're going to be given a graph. So in the handout that I gave you, which will also be found on my math lab, you can print out the graph that was given to you and tape it down. So our job is to find our function. So let's write down as much information as we can about this function. Just by looking at it, we should be able to see that it has vertical asymptotes at x is equal to negative 5. That's this one right here. It also has another vertical asymptote at x is equal to 2. That's this one right here. Now what that means, working backwards, that we must have x plus 5 in the denominator as well as x minus 2 in the denominator. So I'm going to write that down. In the denominator. In the denominator. We also see a horizontal asymptote at y is equal to 2. So that means that we have to have a coefficient of 2 in the numerator and 1 in the denominator. This also means that we have to have the same degrees at the top as well as at the bottom. Okay, so let's see what we have. What we know from f of x is that at the bottom we must have x plus 5 and x minus 2. And notice I have x squared when I multiply these two, so I have to have two things up here as well, or at least an x squared up there. So we're going to see if we can find those in just a minute. Let's go find our y-intercept. Remember, when our y-intercept, we let x equal to 0. And if we look at our y-intercept, we have one right here at 0, negative 2. So somehow, when I get my f of x and I plug in 0 in it, I have to find out that this is going to equal to negative 2. So I put 0 at the bottom, I get 0 plus 5, 0 minus 2, so we can see I get negative 10 at the bottom. So I need to get a positive 20 at the top. So let's see if we can figure that out. So let's see what we can get. We can try to look for our x-intercepts. For x-intercepts, we find the point -2, 0 and +5, 0. Remember, to find x-intercepts, we let y equal to 0, and we literally just let the numerator equal to 0. So we must have had x plus 2 and x minus 5 in the numerator. So I'm going to put that way up here and write down x plus 2 and x minus 5. Those came from the x-intercept. So I'm going to come back over here and I'm going to plug in 0 into there. I'm going to get 0 plus 2 and 0 minus 5, and you see that I get -10 at the top as well. I need to get -2. So the two negatives are going to cancel. I still need to multiply by -2. So I'm going to squeeze in a -2 up here to cause my -2 to come out at the end for my y-intercept. So we have found our f of x that will satisfy this. And again, we can see that at the long run, meaning that when it goes all the way to the end, we can see that it's going to be a negative 1 over x kind of acting thing. In our case, the -2 does make sense. So I'm just rewriting my f of x because we have found it using the information we have. Now, there's more than one answer. What if I multiply the top by 3 and the bottom by 3? I'll still get the same thing. But this is at least the minimum. Let's do one more example. Call this example number 3. Let's say we have a cylinder that has capacity of 500 centimeters cubed. And what we do know is that the top and the bottom of my cylinder cost 0.05 cents per centimeter squared, and the side cost, at least the material to make it, cost 0.02 cents per centimeter squared. That kind of makes sense. That's why it's easier to squeeze the can in the middle than it is the top and the bottom. So our job is to express cost of a can as a function of its radius. So let's first draw a picture of what we're talking about. So here's my can, here's our radius, and notice we have the top up here and we have the bottom down here. Those are done differently. So let's find those first. The area at the top is pi r squared. The area at the bottom is pi r squared. Let's find the area of the side. Remember, that just creates, let me draw it down here. If I were to open it up, it would just create a rectangle. And this rectangle has to go, this part right here, has to go all the way around. So that's actually our circumference, which is 2 pi r. And then we still need to get our height of our can here. So again, we'll find the area of the side. That's going to equal to 2 pi r h. So we got to figure out, we have an h. We don't know what that h is. Well, we know it's the height of our can. So we're going to have to figure out that one. But what we do know is that the volume, so I'm going to write it down here, we know that the volume of the can is 500 centimeters cubed. To find the volume, you get the area of the bottom and you multiply it times the height, and that will give you the volume. So what we're going to do is we're going to solve for h when we know the volume is 500. Solving for h, I get 500 divided by pi r squared. So we're going to use this h in this formula here. So the area of our side is 2 pi r times h. H is 500 over pi r squared. Simplifying this, I get 1,000. The pi's cancel, one of my r's cancel, and I just have an r at the bottom. So this is the area of the side of my cylinder. So now we found the area of the top, the area at the bottom, the area of the side, and now we can use our cost formula to find the equation of cost. So here's our cost, which is going to be dependent on R. I'm going to combine these two and say I get 2 pi r squared times the cost of doing the top and bottom, 0.05. And we're also assuming that R is in centimeters, so that way the units will work out. Plus, I need to add the side, the area of the side, 1,000 over R, times it cost, 0.02. So we have found our formula for that. We can find the cost of a can, of a cylinder can, that would still have our 500 centimeters cubed volume, and then we can pick a value for R and see how much it costs to make that can. So we'll do this part A, and this is part A. Part B is find cost of and let's just pick a number. Let's pick a 10 centimeter radius can. So that just means I'm going to let R equal to 10 and plug it into here. So the cost, if the radius is 10, is 2 pi r squared, it's going to be 100, times 0.05, plus, I'm going to have 1,000 divided by 10, that becomes 100, times 0.02. And now I'm just multiplying. I multiply this times 100, I get 5. 5 times 2 is 10 pi. 100 times this is just 2. So this is how much it would cost in cents, because those are our units. So that's how much money it would cost us to make the can that has the volume of 500 centimeters cubed. And that ends this lecture.